close your eyes and imagine yourself within a supervoid. Darkness envelops you, holding you captive and isolated. With your eyes, even with any amateur telescope, you see nothing. No stars, no hint of the fuzzy smudges we now know as our own neighboring galaxies. To you, the universe is empty. The Boötes void is a spherical region 330 million light-years across, approximately 0.2% the diameter of the entire observable universe. The Milky Way could fit inside it millions of times over, and yet within a volume of about 1 million cubic megaparsecs, where there should be thousands of galaxies, we have observed only 60. Spiral galaxies, blue with the light of new star formation. To quote astronomer Greg Aldering, if the Milky Way had been in the center of the Boötes void, we wouldn't have known there were other galaxies until the 1960s. Indeed, were the Earth to rest on one edge of this void, observers on the other side would only now be receiving light from a time when amphibians dominated the Earth, before even the age of the dinosaurs. Even now, we do not fully understand how such a void came to be. The age of the universe sets a limit for the maximum size of any structure, galaxy clusters, and indeed the voids in between. There should be no single structure in the universe that is already greater than tens of millions of light-years across. The Great Nothing, as the void is known, shatters this limit. Though its absence of structure does give us an insight into the growth of structure at the earliest of times. The few galaxies observed within the void following a tube shape, perhaps the crumbled remnants of a wall between two voids. Individually, these voids would each fit within the growth limit, but together they form a supervoid. And so, even here, in the Great Nothing, one of the darkest places in the universe, there is the light of galaxies, unveiling their secrets to us through the visible spectrum. To find true darkness, we will have to look further than even the Boötes void. Further back in time. We can only find complete oblivion in the time before stars and galaxies and planets existed, forebodingly known as the Cosmic Dark Ages. Here, the darkness was total and long-lived. Although for about 200 million years after the Big Bang, the universe contained a variety of ingredients that could produce the first stars, none formed. There was no visible light at all. But why was the cosmos dark for so long? What does this mean for the stars and galaxies we see around us today? And how can we possibly hope to shed any light on an era when there was only darkness? In 1543, Nicholas Copernicus showed the Earth isn't the center of the solar system. In the 1920s, Jan Oort discovered the Sun wasn't in the center of our galaxy, and in that same decade, Hubble discovered our galaxy was just one of countless others. Cosmologically, we aren't the center of anything, and that is a sobering realization. This video has been kindly sponsored by BetterHelp, and they are here to help you through life's many realizations. With BetterHelp, you can tap into a network of over 30,000 licensed and experienced therapists who can help you with a wide range of issues. You can then talk to your therapist however you feel comfortable, whether it's via text, chat, phone, or video call. With BetterHelp, you get the same professionalism and quality you expect from in-office therapy, but with a therapist who is custom-picked for you, with more scheduling flexibility and a more affordable price. So get 10% off your first month at betterhelp.com/HOTU, and I've also linked them below in the description. Thanks to BetterHelp for supporting educational content on YouTube. In 1995, the then director of the Hubble Space Telescope, Bob Williams, had ring-fenced some personal observing time. He was the envy of the scientific world, holding precious hours on the world's greatest telescope, able to look at anything he wanted. At the time, Hubble was in the spotlight, but not for the right reasons, having used up billions of dollars of public funds only to require a crewed space mission to correct a near-fatal flaw in the system's optics. The mirror, which reflects gathered light into the instruments, needed to be extraordinarily smooth in order for the image to be in focus. Hubble's mirror was very smooth indeed, but the first images had been disappointingly blurry, a devastating blow to the intended science aims of the mission. It was determined that the mirror had an aberration less than a 50th of the width of a human hair that was causing the incoming rays of light to focus at different points, clouding our view of the cosmos. For most space missions, this would have been fatal, but Hubble was in low Earth orbit, making a repair mission not unrealistic. Astronauts installed several clever adaptations and replacements, correcting Hubble's eyesight to perfection. But now, Williams was under pressure to produce something of worth, something that would dispel the naysayers in politics, press, and even within the corridors of NASA. And so he decided to look at nothing. Against the counsel of his colleagues, Williams and his students steered the eye of the billion-dollar machinery such that it looked past the planets, sidestepped the stars, and away from the galaxies. Hubble instead settled its sights on a tiny patch of sky, only 1/30th the diameter of the Moon. And there it stared for 10 whole days. To our eyes and any other telescope that had come before, the patch was barren of structure. But this technology was a giant leap forward in astronomy, and the fine resolution and sensitivity of the Hubble Space Telescope revealed shapes in the darkness. Over a long exposure, the new Hubble could slowly gather photons coming from the farthest and faintest objects in the universe, and distant galaxies of every size, shape, and color emerged from the darkness. We now know this as the Hubble Deep Field, one of the most iconic images in astronomy. As with any photograph, this image is a 2D projection of a 3D landscape. Galaxies far removed in distance appear to be neighbors. It is also a projection of time. Photons from the farther galaxies have traveled for longer, and so we see those galaxies as they were farther back in time. Galaxies can even appear to be colliding when they existed as pictured billions of years apart. To understand why, let us consider the observable universe as constructed of a series of shells around us. The shell closest to us is easy to observe because the light travels to our telescopes almost instantaneously. Light from the Sun takes about 8 minutes to arrive to Earth. Move a shell outwards, perhaps to our nearest neighbouring galaxy Andromeda, and from here, the light we see today has taken 2.5 million years to get to us. Released when one of humanity's earliest ancestors, Homo habilis, walked the Earth. We see Andromeda as it was 2.5 million years ago. This may be a long time for us, but it is still a short time in terms of the cosmological timeline of 13.8 billion years. As we consider the light from even farther shells, the photons we receive get progressively more ancient, and so we can see further back in time. And so with Hubble, we could finally observe light from galaxies as they were only hundreds of millions of years after the Big Bang. So faint and poorly resolved that they are mere red smudges in the sky, just as our closest galaxies were once smudges on the sky for the astronomers of the last century and before. We now have the means to pick apart the light that we observe, working out the composition of that galaxy and comparing known element markers to work out the distance to and age of the galaxies we see. This method uses the same principle that causes a fire engine siren to change pitch as it approaches and passes you on the street. As the fire engine approaches, the wavefronts of sound pile up, and we perceive a sound of shorter wavelength or higher frequency. Conversely, as the fire engine recedes, the wavefronts are increasingly spaced out, and we hear a lower pitch. The inherent siren pitch remains the same, but it is the relative movement between the source and the listener that causes a shift. Now imagine a galaxy as our siren, except instead of listening for the sound, we observe the siren light. This light is a specific color, blue, and does not change. As the galaxy recedes from us, however, the light wavefronts stretch out and we observe a longer wavelength light. The siren gets redder. We call this shifting of the light spectrum redshift. Certain chemical elements are natural siren lights in the spectrum, producing a clear emission line at a known frequency. By measuring how much that line has shifted in a galaxy's spectrum, we can calculate the speed at which it is travelling away from us. Edwin Hubble, the famous astronomer for whom the telescope was named, observed that the further the galaxy, the faster it appeared to be travelling away, a keystone of the Big Bang theory. As a rule of thumb, the oldest light is the most redshifted. In this way, we prize apart the thousands of galaxies that appear tangled in the deep field images, and brush away layers of young galaxies until we are left with only the oldest, the first of their kind. The latest deep field image from the James Webb Space Telescope covers the area of just a grain of sand in the sky, and yet still thousands of galaxies emerged from the darkness, pushing back the cosmic frontier to only a few hundred millions of years after the Big Bang. We are finally reaching a time in the universe where there was no visible light at all, a time that even Webb is blind to. The frontier of the first stars. But does this mean we can go no further? Are we forever closed off from the darkness that came before? In the beginning, light ruled the universe. The energy density of radiation far outweighed the energy density of matter, and interactions between the two were commonplace. So much so that photons of light quickly broke apart any atoms that formed, and as a result, the photons could not travel freely in this superhot, dense plasma of matter. This soon changed, however. While both densities reduced as the volume of the universe increased, radiation fell faster because of an extra factor: the stretching of light into longer wavelengths as the universe expanded and lower equivalent temperatures, cosmological redshift. After 380,000 years of expansion, the energy density of radiation had fallen below that of matter, and the dominion of light in the cosmos was long over. The temperature of the plasma had in fact cooled to such an extent that atomic nuclei could now reliably combine with electrons into simple atoms. Though light was now no longer the dominant force in the universe, there was an upside. The creation of atoms now meant photons had space to travel, having their paths diverted only occasionally through interactions with matter. But what would you have actually been able to see? The answer is hard to know for certain, but we can estimate what the universe would have looked like. The radiation at the point of recombination emitted as a black body, an object that emits radiation across wavelengths with a predictable shape, as long as you know its temperature. To an onlooker, the universe would have seemed to have a warm orange glow. Over the next few 100 million years, as the universe expanded further, the dropping temperatures led that glow to redden with time. Finally, it cooled such that there was no longer radiation emitted in the visible part of the electromagnetic spectrum at all. The embers of the Big Bang faded entirely into the infrared, microwave, and radio wavelengths. Darkness fell. In the midst of the black, however, all was not quiet. For another kind of matter was created in the Big Bang, a kind of matter that is still mysterious to us today. Dark matter. In the 1960s, scientists Kent Ford and Vera Rubin measured the orbital velocities of stars in spiral galaxies and found that something didn't add up. Orbital velocity, the speeds at which stars orbit a galaxy, is a fine balance. Too slow and gravity causes the star to spiral inwards. Too fast and the star overcomes gravity and flies out of orbit. Ford and Rubin carefully estimated the stellar mass and hence gravitational pull of a variety of galaxies and found that the stars were simply moving far too fast. observation after observation pointed to an uncomfortable truth. There must be a hidden component of mass keeping them in orbit. And that hidden mass was known as dark matter. Calculations show that this dark matter makes up 4/5 of all matter in the universe, and yet it still evades our direct detection and capture today. The matter we see around us interacts with the universe both gravitationally and electromagnetically. Dark matter, in contrast, only interacts with the gravitational field. It cannot absorb or emit photons and so has no imprint on a spectrum in the same way chemical elements do. It does possess a gravitational pull, however, and so high-density areas of dark matter can grow and collapse through accretion, but only up to a certain point. And this is key. There can be no stars or planets made of dark matter. As a cloud of matter collapses, the pressure of the particles in the cloud fights back. Pressure is linked to temperature. The denser the particles, the hotter they are, and the more kinetic energy they have to more effectively create an outward-acting pressure force. Normal matter can convert thermal and kinetic energy into electromagnetic radiation via the excitation of electrons in colliding atoms. The atoms move apart at a slower pace, and when the electrons naturally return to their ground states, they emit photons, which carry away the parcel of energy from the cloud. The pressure is reduced permanently. But dark matter does not interact electromagnetically and so cannot emit photons. There is no escape valve. This means that once the outward thermal pressure of the system balances the inwards gravitational pressure, the collapse is simply halted. And so instead, dark matter collapses into filaments, connecting at their densest points into halos. Unable to emit light, our Big Bang observer could not see this vast background web of dark matter behind the uniform orange or red glow of the gas. Even in the total darkness that followed as the radiation shifted out of the visible, the dark matter remained hidden. For close to 200 million years, this remained the state of play, a web of dark matter that was doomed to darkness forever and a mist of gas too dilute to ignite fusion. And so, how could the universe ever form a star to break the impasse? And hidden as the evidence is in the total darkness at the beginning of time, how could we ever know what happened? On the 6th of May 1937, flames viciously engulfed the German airship Hindenburg as it attempted to dock with its mooring mast in New Jersey. Bystanders could only look on in horror. Pride of the fleet, the ship regularly carried passengers across the Atlantic Ocean at a stately 80 miles per hour. This journey had been no different until the very last moment, when the hydrogen cells filling the balloon ignited one by one, causing explosive damage as the fuel tanks erupted. Remarkably, just under 2/3 of the passengers and crew survived, thanks only to its proximity to the ground and the extended duration of the disaster. Most victims, however, were severely burnt, and grief ripped through the families of the 35 lost souls. Airships had been a regular sight across city skies, carrying army personnel, passengers and freight across and between continents. Most airships utilized hydrogen as a way of filling the balloon, as its buoyancy is well above that of air. But hydrogen also boasts another property. It is extremely flammable. Most evidence points to the cause of the Hindenburg disaster as a hydrogen leak in the fuel tanks. When this hydrogen mixed with oxygen in the air, the gas holding up the balloon became ready to blow, and it is thought that a simple flash of static electricity provided the source of ignition, thus ending the era of airships with almost immediate effect. Hydrogen. One proton, one electron. Simplicity itself. This most basic atomic structure is odorless and tasteless, and it will combust when exposed to even the lowest concentrations of air and in ignition. But even that fatal destruction is far from the full power held within this small orbital system. Nagasaki, Hiroshima. These cities act as reminders of the horror that humankind can unleash upon itself just by splitting the atom, fission. But fusion-based hydrogen bombs are far more devastating. They are up to 1,000 times more powerful and could easily kill the populations of entire cities in an instant. And many of the scientists that worked on creating these nuclear bombs were also physicists and astronomers themselves, looking to the fusion of hydrogen within stars for inspiration. But at around the same time, hydrogen became the focus of another group of astronomers, for a slightly less bombastic but no less remarkable reason. Jan Oort had risen to the top of the astronomical world by questioning the assumption that the Sun was at the centre of the Milky Way. He had shown that the Sun was in fact 30,000 light-years out, in a galaxy that was rotating just as a spiral would. Now, however, he was half in hiding, having protested and resigned over the dismissal of his Jewish colleagues. The war was raging, and Holland was under German control. Research and the exchange of knowledge was fraught with risk. But the pull of academia was too strong to keep him solely in his country retreat. For Oort was still in pursuit of a perfect model of our galaxy. But to do so, he had to overcome a challenge. For our Milky Way is shrouded in dust. He would need to pierce through the obscuring interstellar clouds and see further than optical telescopes would currently allow. But how? The answer finally came in a smuggled issue of an astrophysical journal which spoke of the promise of detecting radio waves from the Milky Way. Radio waves have long wavelengths and are immune to the obscuring dust. In addition, the interstellar gas feeding whole stellar nurseries might emit radio waves, illuminating the galaxy on much grander scales than individual stars. Oort realized that with a subtle radiospectral line, he could map our galaxy far beyond the boundaries of optical light. And so in 1944, Oort tasked student Hendrik Christopher van der Helst with searching for a way to determine the shape of the Milky Way by detecting and mapping the invisible hydrogen gas that pervaded it. There are many ways in which an atom can emit light. Tiny transitions of electrons between two energy levels in an atom cause the emission of photons with an equivalent energy, or wavelength. Different processes lead to different wavelengths. Oort and van der Helst needed a transition that was common enough to occur regularly across the sky, and that produced an intensity such that astronomers could clearly measure its spectral line. Having worked meticulously through the atomic transition probabilities, he found a promising candidate. Within the first energy level of the hydrogen atom was a hyperfine structure, a splitting of the energy level into sublevels, populated according to the electron's values of the atomic property spin. If an electron holds the same spin value as the proton it orbits, it occupies a higher energy level. If opposite, lower. Sometimes electrons in the higher energy level spontaneously change spin, in a rare occurrence called a spin-flip transition. The electron moves to the lower energy level, emitting a photon of energy precisely equal to the hyperfine energy gap. This photon has a frequency of 1420 MHz, or a wavelength of 21 centimeters, placing it within the low-frequency domain of the electromagnetic spectrum. Perfect for a radio telescope. Van der Helst presented the 21-centimeter emission line as the key to mapping hydrogen across the Milky Way, a special second sight that would reveal structure far beyond what the stars could tell us. But was the probability of success too low? The probability of an electron spontaneously flipping in spin was minuscule, and so to have such a rare event be detectable, the volume of hydrogen would need to be huge. We can imagine this like trying to find that elusive rare trading card in your trading card collection. If your card makes up 100th of those manufactured overall, you will be lucky to find it in a single pack. Buy several hundred packs though, and the rare becomes observable. the Charizard commonplace. In the mid-20th century, astronomers could not be sure at all of the amount of hydrogen in space, but there was general skepticism that it could be so much as to make the 21-centimeter spin-flip transition observable. Oort salvaged 2 leftover German antennas and set to work. However, though he was a well-respected and expert astronomer, the electrical engineering knowledge required to construct an interstellar listening device was a unique skill, and one that he entirely lacked. And, unbeknownst to them, at the same time a group of physicists in the US had also taken interest in Van der Helst's theory, but with the expertise to follow up. Edward Purcell's head had been turned because of his background in subatomic matter, and his PhD student, Harold Doc Ewan, had a background in radar physics. They too set to work immediately. Ewan used plywood and copper plating, expertly installing the electronics to construct a pyramidal horn radio antenna. These odd-shaped devices, like an ice cream cone on its side, were less susceptible to human-made interference from radios and other electric equipment. The horn was installed hanging out of the 4th-floor window of the lab on campus, the naive scientists not foreseeing the risk that students would enjoy using the horn as a target for snowballs. The device didn't need to be big or steerable, because they would not be scanning across the skies in their search. Whether diffuse or dense, the hydrogen should be everywhere. And so, on Easter morning, March 1951, they successfully detected the 21-centimeter galactic emission line. It had worked. Van der Helst was right. Fortunately, a quick two-way sharing of knowledge began, with the Americans teaching the Dutch how to construct the experiment, and the Dutch explaining to the Americans the astronomical context of what they had achieved. This generous sharing of knowledge meant that, within the space of 3 months, the global radio astronomy community was primed to map our galaxy's hidden corners and far-off lands. By searching for such a specific spectral line, astronomers could now not only identify where the gas lay in the galaxy, but also whether it was moving towards or away from us by measuring the redshift of the light. And it is in this way that radio astronomers first showed beyond doubt that the Milky Way was both a spiral in structure and that it was rotating. Today, we still search for this line using ever more advanced telescopes, reaching further and further and discovering new arms and branches to our home galaxy. But what does this mean for the cosmic dark ages? Radio telescopes give us the means to light up the invisible gas that permeates galaxies. Hydrogen is the most simple of elements and the main constituent of normal matter in the universe. Before planets, before stars, and before galaxies, there was just this gas, flowing through the universe and becoming trapped in the vast web that dark matter had woven. This gas was still there when darkness fell, invisible to the optical onlooker. But look again, with eyes tuned to a wavelength far removed from the rainbow. Look instead with eyes tuned for 21-centimeter radiation, and the universe becomes bright with structure, even during the darkest times. The surrounding hydrogen gas follows where the dark matter went before it, collapsing onto the filaments and halos. Simulations show the hydrogen tracing the dark matter structure almost perfectly under the cover of darkness. And so, we have found the means to trace the earliest stages of star and galaxy formation, a single wavelength of light, 21-centimeter radiation. The universe was dark to our eyes for hundreds of millions of years as the ingredients for star formation gathered and ignited. But with other eyes tuned to longer wavelengths, we would have been able to see these nascent environments and know where the first stars would form. But do the first stars really mark the end of these dark ages? Would darkness really lift with the flick of a switch? Our seas and oceans are the largest habitat on Earth, and one of the most varied. As we snorkel in their crystal-clear waters, schools of brightly coloured fish captivate us. Sinking below the surface, however, our eyes steadily become useless as the sunlight dwindles. By 10 meters down, the reds, oranges and yellows have been absorbed and you struggle to see with only 70% of the surface light. By 50 meters down, the greens and violets have been excised from the rainbow too. And yet still, the ocean descends, and still, life is all around you. The fish even become redder as you fall, evolution having noted that in an environment lacking red wavelengths, they will appear almost invisible. 200 meters marks the twilight zone, a dim, monochrome world. You begin to see the glow of bioluminescent animals such as the hatchetfish float past, creating their own light to match the waters above so that they don't get seen and snapped up by predators below. At 300 meters, you are enveloped in darkness, working with only the light of a moonlit world on the surface. A giant squid glides serenely past you, all 10 meters of it, its football-sized eyes scanning you for threat. At 850 meters, your eyes can no longer gather enough paltry photons to activate the optic nerve. The midnight zone begins, and in some places may even continue for several more kilometers. On Earth, then, life has adjusted to total darkness and learned to live despite it, hidden from the only way our eyes know how to look. And so, during the dark ages of the universe, we know too that the black was not empty. There was structure in place behind the scenes, a dark matter web that drew in nearby hydrogen and built the foundations of the universe, brick by brick. And all over the universe, by about 200 million years after the Big Bang, gravity would crush these dense pockets of hydrogen just enough to ignite the engines of stars. In every direction, the lights blinked on, slowly illuminating the Dark Ages. But was the oblivion that preceded this visible illumination really so empty of light? It may have been dark in the optical, but was it truly dark in other wavelengths too? Despite emitting across all the wavelengths of the electromagnetic spectrum, the first stars found their nascent cries muffled by the murk of a deep ocean of hydrogen. The path was not entirely clear for this new light. While gravity had swept some hydrogen up to make the first stars themselves, there was more than enough remaining to swaddle the newborns. As the first engines of fusion started up and the resulting photons found their way out from the core to the surface of the star, they encountered clouds of atoms, ready to absorb them before they could make it much further. An observer of these first stars would likely notice little wrong with the light, as hydrogen absorbs only 4 visible wavelengths. The rainbow of its visible spectra would therefore be complete, except for discrete emissions within the red, cyan, blue, and violets. At the lower wavelengths into the UV, the first stars emitted strongly, but a removed observer, whether a human equipped with a telescope or an insectoid with UV-sensitive eyes, would have seen a dimmer star. But before too long, these first stars began to change their surroundings, and in a surprising way. Our traditional view of an atom has been passed down to us from the early 20th century physicist Niels Bohr, a compact nucleus of protons and neutrons orbited by satellite particles, called electrons. But that is not how many of the atoms in our universe pass their time. Almost 99.9% of the matter in the universe is in the form of a plasma, a mix of separated electrons and ions. The highest energy level in a hydrogen atom is 13.6 electrovolts. If the atom absorbs a photon carrying more than this amount, the electron is energized to such a degree that it overcomes the bond with its proton and becomes an autonomous, free particle. The hydrogen atom is said to be ionized. In the immediate aftermath of the Big Bang, the high temperatures and frequent collisions rendered all normal matter ionized, before it cooled and came together as full hydrogen and helium atoms with their requisite electrons at the beginning of the Dark Ages. But not for long. For quickly following the end of the Dark Ages is a new stage in the history of the universe. The era of re-ionization. The first photons from a first star and later a first galaxy ionize their immediate surroundings, creating a shell of ionized hydrogen through which the next photons can get a little farther before they meet an intact hydrogen atom. Over time, these bubbles of ionized hydrogen get larger and larger, connecting and merging such that the hydrogen gas that we observe around us today is almost all ionized. It is still a mystery exactly how the universe got to be in the completely ionized state that we observe it in today. The first stars could not produce enough ionizing photons in their short lifetime to fully clear the way. Instead, it seems more likely that, while the first stars began the process, it was the first galaxies that finished the job. Full of the many and long-lived second-generation stars and a central black hole accretion disk spewing radiation, they could easily ionize the universe before the first billion years of time had passed. Then, 1 billion years after the Big Bang, in a universe full of ionized gas, light could travel with the same freedom it can today. The epoch of re-ionization was complete, and with it, the Dark Ages was truly over. Together with the Dark Ages, the epoch of re-ionization is an almost totally missing era in the timeline of our universe's evolution. There have been a handful of galaxies observed within the latter epoch, but not enough to make anything but the most tentative scientific conclusions about the state of the universe over the whole era of the first stars. Doing so would be like making conclusions about the entirety of human history based on a single bone from each of 5 random centuries. And so when the James Webb Space Telescope launched on December 25, 2021, expectations were high that we would see many more galaxies from within that lost time. For Webb is infrared, allowing it to probe even further back in space and time than Hubble. When we peer at the Hubble Deep Field, we can see a range of galaxies from many epochs, the oldest visibly reddened because of the expansion of the universe, redshift. But while galaxies emit across the electromagnetic spectrum, as we observe the spectrum of light from older and older parts of the universe, there will be a point at which most of the light has redshifted out of the shorter wavelength domain. Hubble cannot produce images of galaxies whose spectra have redshifted out of the visible wavelengths. Webb, however, an infrared instrument, can see light from further into the past, because it can still detect the photons even though they have redshifted out of the visible wavelengths and into the infrared. Able to look deeper and farther than Hubble, Webb has already observed some of the earliest galaxies we have ever seen in the universe, barely 350 million years after the Big Bang. But even this Goliath of astronomy has a limit. While Webb has provided a fascinating insight into early galaxy formation, to reach further back, to reach the mysterious Dark Ages, we need a different instrument entirely. Hubble, an optical telescope, and James Webb, an infrared telescope, ultimately provided tiny samples of the sky, both in image space and across time. To push further to the earliest moments of the epoch of re-ionization and the Dark Ages requires the longest wavelengths we have: radio. As we look further back in time, we observe more of the universe per pixel. Thus, while we may be able to see the Sun and galaxies such as Andromeda and the Whirlpool in exquisite detail, as we move to the earliest times, the resolution achievable is simply so low that we cannot see individual stars or even individual galaxies. We need something on a much larger scale, and radio loud. And this is where Van der Helst's Hydrogen-21 line comes into its own. As we have seen, in the early universe, clouds of hydrogen pervaded the cosmos, and these can provide a means for us to observe the progression of the epoch of reionization, the 21-centimeter line. We can observe the Dark Ages as a cacophony at the redshifted 21-centimeter wavelength. Then, as the ionized bubbles grow and merge, we can trace them in the absence of 21-centimeter radiation, like a cosmic Swiss cheese. The shape and speed they grow can tell us much about the sources that are producing the radiation: population 3 stars, baby black holes, and even the earliest forms of galaxy. Radio telescopes hold the key to lighting up the Dark Ages, but the experiment itself is one of the hardest in astronomy. The signal is incredibly small, buried under the photons of our bright galaxy that cannot help but fall on the same antennas. And so, is it even possible to find this signal of reionization and illuminate the Dark Ages? Imagine yourself deep in the Australian outback, in a desert landscape void of human life, the red dust broken only by rocks and desiccated shrubs. The powerful heat of the day shimmers in the dry air, no hint of recent or forthcoming rain. But as you walk, you see evidence of life. Sheep and cattle grazing on a land that humans largely find too hostile to occupy. And these animals don't just experience this land differently, they see it in an altogether different light. The lenses and sensors embedded in our retinas can result in vastly different views and understanding of the same environment. Humans are usually born with color-sensitive cones tuned to red, green, and blue, but the cows and sheep you pass cannot see the shades of red land at all. The snake that slithers past your feet also lacks the ability to see shades of red. But it has an ability you do not, the ability to sense infrared. Here you find another companion as a scorpion scuttles in front of you. This scorpion can detect UV light too, and even has the rare quality of fluorescing when exposed to these wavelengths. The animal kingdom is alive with examples of adaptations to different levels and wavelengths of light. Indeed, humans are rare for only seeing in the optical. Instead, we have emulated the animal kingdom by creating technology to help us perceive our environment in the UV, infrared, and X-ray wavelengths. We have also invented entirely new methods, not shared by any other being on Earth, to access the longest wavelengths, the radio waves. In the pursuit of long-distance communication, we built our own interface with the radio universe, learning through trial and error how to listen in to a signal from a different room, a different country, a different continent, and then, quite by accident, we picked up the signals of the stars and planets and meteors, and radio astronomy was born. We had developed the means to communicate to the distant universe and into the distant past. Only humans can communicate at these longest wavelengths, having carefully created for themselves a new kind of eye. As you walk on through the outback, you come across a strange sight. Standing on the dirt lie strange metal sculptures. Some are bow-tie shaped, some look like reflective tables, and others look a little like trees, their spikes evoking cacti. But these bizarre metal structures in the Australian outback are not discarded abstract art. They are an interface to a universe that only we have access to. They regate to the past, to a time when the stars were only just forming in the densest nodes of that dark matter web. Humanity has also woven a web, creating societies and cities that spread out across the Earth. This spread, however, is not even. Civilization built up around rivers and seas, driven by a need to trade. Over time, the harsher terrains, like the outback, were abandoned for the promise of amenities and safety in numbers. And for radio astronomers aiming to detect the weakest signals from space, the emptiest voids on Earth are an ideal location to set up their experiments. Deep in the Australian outback, covering an area of 49,500 square kilometres, the Murchison Shire hosts a population of just 100 people. Here, in one of the quietest places in the world, away from human technology and interference, radio astronomers have spent over a decade searching for signs of the Dark Ages. And in 2018, one of these telescopes received a signal that was very strange indeed. This telescope is humble, simple even, and far from the standard image that we associate with astronomy. For EDGES is a radio telescope. Short for Experiment to Detect the Global Era of Reionization Signature, EDGES works like a TV or radio antenna, receiving radio waves and converting them into a digital signal. It is a sensor tuned to that cosmological 21-centimeter line emitted from the era of reionization and the first stars. These photons have been traveling to us from 13.7 billion years ago, redshifting such that we detect them at wavelengths stretched from 21 centimeters to about 2 meters. By building a telescope to this scale, those wavelengths create a voltage across the telescope, producing a digital signal that we can examine for its provenance and its intensity. EDGES, in effect, measures the temperature of the hydrogen across the Dark Ages, retuning and reobserving at different wavelengths to scan photons from across hundreds of millions of years. Though in the beginning the gas is cool, coalescing around the dark matter web, when the first stars form and begin emitting radiation of their own, they heat their surroundings, imprinting a change in the 21-centimeter signal. Never moving, never making a sound, its human operators thousands of miles away, EDGES listened patiently. By observing at different wavelengths, the telescope could probe further and further back through the Dark Ages, looking for any sign of the first stars forming. The data was untidy. The imprint of the electronics of the telescope and radiation from all around our local galaxy had to be modelled and removed carefully to see if there was a quiet whisper underneath. The team of astronomers found they could recover a signal below all the noise, a change in temperature at approximately 180 million years after the Big Bang, potentially the first direct observation of the era of the first stars. A birth certificate. This discovery alone was momentous enough to revolutionize a field starved of data. But there was more. The temperature of the gas was all wrong. The data suggested that the gas in the universe during the Dark Ages was far colder than any model had predicted. Every model of our universe, developed over decades that fit all other observations, was suddenly useless. Astronomers were shocked, and there was years of speculation as to the cause of this unexpected cooling. Perhaps there had been errors introduced in the data during the cleaning of the radiation picked up from the galaxy. Perhaps this coolness was an illusion, and there was a mysterious background of radiation that was leading to the gas seeming cooler. Or perhaps, and most sensationally, dark matter could interact with the gas in early times, cooling it down through collisions. The claim was that in a cooler universe, dark matter behaved differently. This was an extraordinary idea, and astronomers met it with healthy skepticism. The need for more evidence spurred the conception and production of a fleet of new telescopes around the world, all aiming to validate the EDGES result. However, with time, there was more and more focus on the first and most mundane explanation. The analysis was simply incomplete. The mysterious signal was noise that had not been correctly removed. The EDGES team had carried out their due diligence, checking all they could, but it was only with wider community help that they could try alternative observation and analysis methods that could reproduce their own result. Saras, an antenna floating on an Indian lake, was the first experiment to confirm with sufficient confidence that the EDGES result was not to be trusted. They couldn't find such an extreme signal. And so the old models were retrieved from the rubbish bin, and calm was restored. But what about the birth date of the first stars? Is it 180 million years after the Big Bang? Can we trust edges enough on this at least, if not the exotic nature of dark matter? The search is far from over. The Dark Ages signal is hundreds to thousands of times smaller than the radiation from our own galaxy, and the experiment is one of the toughest in astronomy. Edges and Saras have begun that search, testing methods and new technology, exposing problems in our theories. Indeed, in that same outback, the Murchison Wide Field Array has been listening for the bubbles of the epoch of reionization using bow tie antennas, called the ear that listens to the sky by the local indigenous people who have granted the use of their land. Soon, both are to be joined by the most ambitious radio astronomy observatory ever built. The square kilometre array is to comprise 130,000 antennas spread across the Murchison Desert. This telescope is so sensitive that it could hear an airport radar signal on a planet 10 light-years away. And it can look back across the first billion years of our universe into the epoch of reionization and the Dark Ages. Despite being one of the quietest places on Earth, the sound of humanity and the interference of the atmosphere is still too great for us to look back into the oldest stages of the Dark Ages. While we continue gathering data, improving our models and methods, we must also look to the next step. We look for quieter places, such as the Moon. Indeed, testing has already begun to aid the sending of antennas to the far side, using the Moon itself as a shield against the onslaught of mobile phone, radio, and satellite signals. And so the universe was dark for almost 200 million years, but really only to our eyes. To the metal antennas in the desert, our interface with the stars, there was never darkness, just a time of quiet industry. The gas and dark matter worked together to form stellar nurseries, and in the longer wavelengths the universe was bright with 21-centimeter photons throughout. But it was the light bursting forth from the first stars that changed the universe to that we now perceive. Those stars would in turn come together to form galaxies, long-lived and bright. The cosmic Dark Ages would eventually meet their end. You've been listening to the entire history of the universe. Don't forget to like and subscribe and leave a comment to tell us what you think. Thanks for watching, and we'll see you next time.